Hello, my name is Charlotte Trujillo. I'm a mechanical engineer with a minor in mathematics, and I'm also the project lead.
Hi, my name is Ryan Sweetman, and I'm a mechanical engineer.
Hi, my name is Emerson Langham. I'm a mechanical engineering student, and I'm the team procurement lead.
I'm James Hart. I'm a system engineer with a minor in aerospace.
Hi, my name is Stefano Figueroa. I'm an electrical and computer engineering student.
Hi, my name is William Hentig. I'm an electrical and computer engineering student.
Just a brief overview on our Design Day poster, which will be present at this Design Day. We have decided to include an overview and scope, some of our goals, the final design that we went with, the progress of our drone, some diagrams, as well as the image of the mechanical design we have gone with, and lastly, a conclusion of everything we've completed. The scope of this project is to take an existing black bar unmanned aerial vehicle, model named Storm, and integrate vertical takeoff and landing capabilities while still maintaining a similar footprint.
With our sponsor, our team developed 8 functional requirements for our system. Stormbreaker shall be assembled and disassembled by hand without the use of hand tools. Stormbreaker shall interface with the existing Storm airframe. Stormbreaker shall perform both vertical takeoff and landing. Stormbreaker shall transition to and from vertical and horizontal flight. And finally, Stormbreaker shall perform horizontal fixed-wing flight. From these requirements, our team developed 4 major categories to base our system-level requirements from: weight, assembly, flight characteristics, and repairability and replaceability. This is our system block diagram that was developed in the early stages of our project. The dotted line shows the system boundary. The internal components are the controller, propulsion, airframe, and power. The controller is the brains of the system and controls elements such as the auto-stabilization. The propulsion contains the motors and propellers that provide lift to the system. The power distributes power throughout the system through a power distribution board. Then the airframe contains the control surface of the systems such as the ailerons and the elevator. Externally, the system will be interacting with the user and receiving commands from the ground control station.
One of the major goals we set ourselves in the development of Stormbreaker was maximizing the torsional rigidity of the VTOL motor mounting system. A major benefit of a rigid system is that it lets the VTOL stability algorithm work more effectively. The more correlated the motion of the gyroscope and the fuselage is with the VTOL motors themselves, the more precisely the aircraft can control its motion while in vertical flight mode. This translates to more pilot confidence and better performance in windy conditions. The agreement we reached with Blackbar was that a plug-and-play option was preferred, where the system could be removed altogether to revert to the Storm configuration. The rethought design is what we call the X-brace. This is a 3D printed component that attaches directly to the underside of the fuselage, bolting directly to the existing payload bolt pattern. This rigidly controls the motion of the individual VTOL motor spars, as well as routing the motor cables directly into the fuselage to decrease parasitic drag.
The first step in our prototyping phase was to take all of our electrical components, wire them together, and secure them to a board in order to test that they are properly working and drawing the correct current and voltage that is required for testing. Once the electrical components were working, we then mounted them onto our first unmanned aircraft system to try and achieve flight. We soon learned that the motor mounts that we had designed and 3D printed could not withstand the torque that was being generated by the VTOL motors and would continuously break or snap on us when we tried test flighting. We were able to design these motor mounts that were able to withstand the torque of the motors and finally gave us our first successful lift of the aircraft. As you can see, the aircraft begins to spin after it has achieved lift. This is because the airframe would twist and the motors were designed to stabilize the flight in order to keep it smooth and go straight into the air. After doing testing with our first airframe, we then moved on to testing with our final airframe. We first tested the airframe with no wings in order to confirm that the VTOL motors would just lift the airframe alone. We then moved on and began testing with wings, slowly incrementing the weight as not to burn out the motors or the ESCs. Finally, we put the wings and tail section to test a fully integrated aircraft. As you can see, the drone struggled to get off the ground. This led to our group purchasing a stronger motor for our final testing.
We had 5 requirements that called for testing to verify: the ability to land in a 20-foot by 20-foot zone, a flight endurance test of 30 minutes, a flight ceiling of 1,000 feet, and flight speeds of 70 knots dashing and 30 knots at cruise. Unfortunately, during this testing process, in spite of more powerful motors equipped, flight with a full integrated airframe was not achieved. The same is true for flight with the removal of the tail. However, flight was achieved with standalone VTOL systems. Due to this result, we believe that the likely complication is overstress on either the battery or the ESC due to weight and or additional drag added by the wings and the tails upon takeoff.
In conclusion to our semester and project nearing completion, we wanted to give a quick final rundown of what exactly we accomplished this year. We have successfully integrated Blackbar's Storm aircraft with a VTOL mountable system. This will allow the Storm a new ability to now vertically take off and land, making it a much more versatile aircraft. This was accomplished, as you saw earlier, by using a mounting system under the aircraft's airframe, which booms would extend from. The end of the booms had the VTOL motors mounted onto them, achieving the VTOL capability we set out to get. We also successfully accomplished several functional requirements we set out to achieve last year. We were able to assemble the Stormbreaker by hand and disassemble by hand, achieving both the assembly and disassembly goals. We were also able to stay under the maximum motor weights by not exceeding the max motor weight we set out to be last year. Similarly, the total aircraft weight was kept under 20 pounds, allowing it to remain as a Class 1 aircraft. We also did have a couple unsuccessful tasks. At the time of the video, we were unable to successfully complete our flight characteristic testing, such as maximum altitude, dash speeds, cruising speeds, and consistent takeoff and landings. This was due to issues with our power system when we set out to perform testing at our sponsor's location. We are still working on solutions to perform the testing procedures, but at the time of the video, we do not have these solutions and testing procedures completed. Finally, we would like to make some final remarks about the project. We would want to look more into improving the aerodynamics of the craft, as many of the booms create a lot of increased drag and weight. If we were able to somehow get these booms to fold after transitioning in the air, or maybe place them within the wings of the aircraft, this may drastically reduce the drag of the aircraft. And finally, we wanted to say thank you and that we look forward to seeing you on Design Day.